So again, I spent a little bit of time talking about the defense in depth, so I don't want to spend a lot more time, but I do want to make a comment. Again, we spent a bit talking about this whole containment design where you have the fuel, and then you have the reactor coolant pressure boundary, and then you have the containment liner, and then the containment structure itself. So I don't want to spend any more time on that. But the actual defense in depth philosophy extends well beyond just these design parameters. We design reactors with a high degree of safety margin built into them just in their normal operation. Further beyond that, we actually test them and we monitor them quite closely to be able to detect in advance of degradation of pieces of equipment or degradation of operating margins. So that's what we're trying to represent here. Furthermore, we design in active systems and components and passive systems and components that in the event that there's an upset condition, for example, I talked about before, let's say that a pipe were to break inadvertently inside containment, we put systems and components in place to be able to deal with the likelihood or the potentiality that indeed we might have an accident on our hands. And furthermore, as we've learned more and more over the years, even though we can design and we can try to put in place as many precautions and pieces of equipment to deal with the consequences of these accidents as possible, there's always the possibility that we could find ourselves well outside the design basis, and we need to be able to deal with and manage severe accidents. And so there's procedures and there's equipment that are typically staged to be able to deal with severe accidents. And again, the concept is let's try to put as many defensemen as possible between the shot on goal and the goal. And again, the objective at the end of the day is to protect the public. So that's the whole defense in depth philosophy. Again, why do we need defense in depth? Unlike thermal power plants, when you hit the stop button, nuclear power plants, even though the nuclear process stops almost immediately, we're still left with the ash, these fission products that I discussed. The fission products themselves are intensely radioactive, and indeed we want to make sure that that radioactivity doesn't get to places that we don't want it to be. Most notably, we don't want it out in the environment. And so what we need to do is we need to be able, and those fission products is part of the radioactivity, they create a tremendous amount of additional heat. And so at the end of the day, we basically have to be able to accommodate that heat even once we hit the stop button for a nuclear reactor. You can imagine if you put a pot of water on your stove and you let the pot boil dry and you have the heat going on there, that pot is going to heat up and eventually it's going to turn red hot. Well, nuclear power plants are no different. If you don't get rid of the heat, these fuel assemblies are going to overheat. The cladding, this tubing that I mentioned to you, is made out of a material with zirconium in it. And zirconium has some very attractive nuclear properties, but one of the downsides to it is that when it gets to a certain temperature, it will take the oxygen out of, remember water is H2O, back from your chemistry class. It will take the oxygen out of the water and it will in and of itself almost turn into a powder, and then you're left with the hydrogen that's left in the water. And so one of the unfortunate disadvantages of the zirconium that's in the reactor is that if we allow it to overheat, it will actually create hydrogen in the process. And so we need to make sure that under every circumstance that we keep the core covered with water, to keep it cool, and to prevent the generation of hydrogen. And so what it amounts to is that when we are preparing and designing for some of these accidents, we design it around the idea of the first and foremost priority is to keep the reactor core covered and cooled. Because if we can do that, everything else will take care of itself. And so all of the systems and all the engineered safety features and all the design barriers are really built around keeping the core covered and cooled. Beyond that, then, our next priority is trying to prevent any radioactivity that may escape, keeping it from getting in contact with the public, and then the third priority is keeping the people that are operating the power plant as safe as possible. So let's talk about, for just a moment, some of the highlights, some of the things that have been in the press over the last 25 or 30 years. 3 Mile Island was a pressurized water reactor, or is a pressurized water reactor. Unit 1 continues to operate quite nicely in the United States. 3 Mile Island Unit 2 was actually a brand new nuclear power plant. It had not even been in service for a year on that fateful day, March 28, 1979. What started out as I certainly wouldn't characterize it as a normal transient, but it's something that is generally expected to happen fairly frequently in the life of nuclear power plants. There were some technicians that were doing some work on some equipment on this secondary loop, and what happened was they inadvertently shut off the water going into the steam generators. Normal plant systems responded exactly as they were designed to and intended to. The reactor shut down as it was expected to. But unfortunately, one of the things that happened was these safety valves, called the PORVs, the pilot operated relief valves, opened in response to an overpressure condition, exactly the way it was designed and exactly as anticipated. The problem was that the valves did not shut. They stuck open. And so what happened was you have a situation where, again, this closed loop reactor coolant pressure boundary that we talked about that actually serves as one of the barriers in the defense in depth philosophy had a leak in it, effectively is what it amounted to. And so they were losing reactor coolant from the pressurizer out these valves into the pressurizer relief tank. Now the PRT is actually, again, I apologize, the alphabet soup of nuclear power. The PRT is actually not a large tank. It's only about 5,000 gallons. And as that high temperature water got in there, eventually the relief, the rupture disc on the tank ruptured. And so effectively we were venting reactor coolant from the pressurizer into the containment building. Now, you see here I highlighted a very important point here. Unfortunately, the reactor operators misdiagnosed what was going on. And indeed, what they thought was happening was, in fact, the reactor was filling up. That not that the inventory was reducing, that the reactor was filling up. As you can imagine, with that valve open, the pressure inside the system began decreasing. It reached a safety set point that caused a safety injection, where all the engineered safety features and all the emergency backup pumps and systems kicked on. And now, so you have all these pumps now that are injecting massive quantities of water into the reactor in response to this dropping pressure, but the reactor operators actually thought that the system was full. So their first reaction was, oh my gosh, we don't want to overpressurize the system, so let's go turn off all the pumps, which is exactly what they did. Now, because they didn't realize it, indeed they had a leak. So what happened was they secured all the injection of water into the reactor, this leak continued, and as we talked about before, basically what happened was they eventually lost inventory in the reactor vessel, the fuel got uncovered, they were no longer able to remove the decay heat, the cladding overheated, it took the oxygen out of the water, created hydrogen. Now the hydrogen that was being generated here inside the reactor, it was venting out into containment, and at one point there was actually a small hydrogen explosion inside containment. All happened within a matter of hours in this reactor. The consequences was major fuel damage. I think the estimates were half to about 2/3 of the core melted. Again, I mentioned that there was a hydrogen explosion inside containment. The reactor containment building actually served a very valuable purpose because it was able to contain that hydrogen explosion, and the off-site releases of radioactivity to the environment were actually quite modest in comparison. Took 14 years to clean it up. They started the cleanup process in August of 1979, and they actually wrapped it up in the summer of 1993, and it cost about $1 billion US. And probably one of the most tragic aspects of it, this was a brand new power plant that hadn't even been operating for a year. And subsequently, it's now been shut down and decommissioned. Unit 1 continues to operate. But that's the story of 3 Mile Island. Started out with a normal plant transient. It was an operator misdiagnosis that ultimately translated into a tragic accident for this power plant. Chernobyl, we've heard a lot about Chernobyl over the recent months. I have talked a little bit about the basic design of the RBMK reactor, so I won't go back and talk about it. But again, what I think is probably one of the most interesting relevance was there were some shortcomings in retrospect in the fundamental design of the RBMK reactors. But let's not forget, RBMK reactors had been operating for quite some time, quite successfully. And indeed, even after the Chernobyl event, they operated quite successfully for a number of years. But what happened was, in the tragic aspects of Chernobyl, were the operators were actually running a test that morning in August of 1986. They had planned a test where they were going to lower the reactor power level down to a certain point. And what they wanted to do was shut off these pumps to see how long it took the pump to coast down without power going to it. They lowered the reactor down into a condition that was extremely unusual for that power plant. And indeed, it was in such an abnormal condition that under normal circumstances, the automatic systems would have shut it down. So in order to run the test, what they actually had to do is they actually had to go in and bypass, physically install jumpers and remove all the engineered safety features that had been built into this power plant in order to run the test. Otherwise, the safety systems would not have allowed them to do that. So they put the plant in an abnormal configuration. They bypassed the reactor protection system. And then one of the other fundamental aspects that I mentioned before, this reactor, because of the way it was designed, it actually, most modern reactors that use water as both the coolant and the moderator, when you lose the water, it causes the reactor process to actually start to shut down. But in this reactor, since they had graphite in here to aid the reaction process, what happened was when they lose water here, it causes the reactor to increase in power. And so what happened was they lowered the power, they bypassed all the reactor protection systems, they began the tests, so they shut this pump down, and all of a sudden with the reactor at a very low power level, without any coolant, with a reduced amount of coolant, they actually voided the reactor. There's a steam, increase in steam inside the reactor. I indicated to you that in this style of reactor, the water actually acts as a poison. So as you remove the poison from the reactor power starts to increase. And indeed what happened was there was a massive explosion inside the reactor. It all happened in the blink of an eye. And so in effect, they did this to themselves by running a test that caused the reactor to run away. And by having bypassed all the engineered safety systems and the reactor protection systems, there was nothing in the way of this reactor exploding. And you can see the photo here that was taken a few days after the accident. Literally, the reactor explosion lifted this shield block, and I don't remember some of our other experts who are here today. This weighs some 3,000 tons, the shielding area. The reactor explosion lifted this shield block up off its pedestal in the first explosion. The pedestal then, when it came back down after the explosion, landed on the reactor, caused a secondary explosion, and you see the results here. End consequences, 64 direct deaths. These were the people that you heard were the liquidators who were assigned to go up on the adjacent buildings and shovel reactor debris back inside the hole. The World Health Organization estimates that there was about 4,000 latent cancer deaths due to the iodine and the cesium that was ejected into the countryside, and about 100,000 square kilometers of the countryside of Central Europe were contaminated. So that was Chernobyl. Again, similar to the 3 Mile Island, self-induced. And our most recent event, the Fukushima Daiichi. Again, this Fukushima Daiichi is a boiling water reactor. There were 6 power plants at Fukushima Daiichi. There were some GE designs, some Toshiba designs, and some Hitachi designs. But fundamentally, they were all basically the same. There was a GE BWR with a Mark I containment. Just to walk through the sequence of events, and you see my little defense in depth chart here. The event actually started off, again, tragic earthquake, but the event in and of itself was well within the design basis of the power plant. So the earthquake caused a loss of off-site power because it damaged the electrical grid off-site, as well as the reactor in reaction to the earthquake. It actually shut down, the emergency diesel generators kicked on, and they actually were operating, of course, in an abnormal situation, but in a very controlled and something that every nuclear operator has done on the simulator 1,000 times. So here they were operating in a normal situation, and then the earthquake kicked them out here into a situation where the engineered safety features were the line of defense that they were operating on. They were sitting there operating on the emergency diesel generators and the backup system, injecting water into the reactor, normal post-accident, post-scram type of situation. Unfortunately, then, about 46 minutes later, the tsunami hit the site. And as we've all come to know now, the emergency diesel generators were actually below grade. The tsunami hit, the emergency diesel generators were inundated with water, and they shut down. So while they initially were operating right here, operating on the engineered safety features well within the design envelope, now all of a sudden, without emergency diesel generators, they're actually that jettisoned them out of this ring of defense in depth, and now they were operating in a severe accident scenario. And indeed, we've known for more than 30 years that one of the 2 highest likelihood core damage frequency events for BWRs is in fact a station blackout. And this is where they found themselves at Fukushima Daiichi with 3 plants in a station blackout scenario. Without electrical power, the engineered safety features are virtually useless. Now, a BWR, in contrast to a PWR, actually has a very, very important safety system that's, at least in units 2 and 3 at Fukushima Daiichi, there are steam-driven pumps that are available to inject water into the reactor, because as they inject water into the reactor, the water turns to steam, and then the steam is siphoned off to run the pumps. It's a steam-driven pump. BWRs are very unique in this regard. PWRs do not have this capacity. A station blackout in a PWR like Daya Bay is a much, much, much more significant event than in a BWR. But unfortunately, what happened is we found out in Fukushima Daiichi, most nuclear plants are designed for either a 4-hour or an 8-hour coping scenario for a station blackout. As we know, in Fukushima Daiichi, it took them almost a week to restore offsite power. That situation was well beyond the design basis of any severe accident scenario that had ever been contemplated for nuclear power plants. And so unfortunately, the situation here, without the ability to inject water, at some point the core boils dry. Again, same process, the zirconium rods overheat, they take the oxygen out of the water, you're left with hydrogen. And in a BWR, at some point they actually have to create a leak in the reactor coolant pressure boundary to lower the pressure to be able to inject water. Which is what they did, which is subsequently how they were injecting firewater, using firewater pumps to inject water into the reactor. That leak that was created actually vents the steam down to the torus. The torus overheats and vents back into the primary containment. Now, primary containment is overpressurizing. They have no way to cool it. They have to open the vent valves on primary containment, which again now, because the reactor core is damaged and overheated, is a steam-hydrogen mixture at very high temperatures. The piping that vents the primary containment, which is this upside-down light bulb-shaped thing, the ventilation system runs through the reactor building. As soon as they open those vent valves, they basically admitted a steam-hydrogen mixture into the ductwork inside the reactor building, and as soon as that met an oxygen environment with a spark, we saw the massive explosions on the news. And those explosions basically damaged the reactor building. One other point of note, these reactors are designed to have the spent fuel. They're actually at this grade inside the reactor building. And there's some design considerations why that is. If somebody's interested, we can discuss that later. But this top portion of the reactor building is actually nothing more than a steel shed. It's really designed to protect what's inside from rain and from the elements. But so when you see photos of the explosion, that's what you've seen is that the steel structure was basically just blown to bits and all the components inside collapsed. But that was the event. Initiated by a station blackout, as we talked about, the reactor core ran dry because we were unable to inject water. Created hydrogen released to protect this primary containment, ultimately resulted in the massive explosions that we saw. Ultimately, we know now about 700 square kilometers of the countryside of Japan were contaminated, again with cesium and iodine. So just to wrap up, these are my views, not necessarily endorsed by the hosts of our event. Nuclear power is truly an amazing technology, but it is extremely unforgiving. It is one of the few ways that we can generate massive quantities of electricity without any greenhouse gas emissions. Globally, on a comparative basis, it has a very impressive safety record. Generally, it can be done economically, certainly in line with other sources of similar scale generation. But managing a nuclear power station is not for the faint of heart. Some of the articles that you may have seen that I've contributed in the New York Times and on CNN, I am a very critical observer of TEPCO. Nuclear power demands the highest standards of operational excellence, and it demands an unwavering commitment to safety in operations. And if you're not prepared to step up as a nuclear operator, then you have no business being in the nuclear power business. And unfortunately, when things go bad, they go really bad inside nuclear power. And you have to manage it with expertise and skill. The other point here that I know some of my esteemed colleagues on this panel this morning will take an issue with on me, but I can tell you, it doesn't matter how sophisticated the reactor design, poor management of any technology will render the design features completely irrelevant. And that's why, in my view and in my estimation, you hear people out flogging these new advanced reactor designs that are passive and things like that. It's a red herring. You give me any reactor design, no matter how primitive or how advanced, I can operate a 1960s vintage GE BWR-1 with a Mark I containment, I can operate that just as safely as I can in EPR. And I can cause just as much damage to the general public and to the countryside with an EPR with poor management and poor operation as I can with the Mark I reactor. Again, we talked about lines of defense and the severe accident, and what we're beginning to learn now is that in Japan that they really didn't take severe accident management seriously. And one of the things that we've learned is that this is a critical component of the defense in depth philosophy. My last point here, I talk about, do you trust your friendly neighborhood nuclear operator? And one of the pieces of feedback that I got yesterday, which is absolutely relevant, and what I should say is, do you trust all of the institutions and all the people that are involved in safely operating nuclear power? Talking about your government agencies and the reporting agencies, the oversight agencies and people like that, because it's an institution as a whole. And do you trust them to look after your interests? Radiation and radioactivity, we can't sense it, you can't smell it, you can't see it, you can't feel it. For example, in Chernobyl, how we ultimately found out and how it was revealed that the accident at Chernobyl happened, it actually happened about 3 days after the accident. At the Oskarshamn facility in Northern Europe, workers were coming to work contaminated with radioactivity 3 days after the Chernobyl event happened. And when they began investigating how workers were coming to work contaminated, what they realized was that it wasn't at the facility that the workers were getting contaminated, they were getting contaminated at home. And when they started the authorities started piecing together all the different elements, what they realized was that something was happening in Eastern Europe. And again, of course, then what we know all is history. So at the end of the day, it's not about the technology. What it's about is about the people and the institutions that are operating it. And so the question is do you trust the people that are operating it? So with that, I will close up, and I guess we're going to take questions later on, right?
Yes.
Or do we have time now?
Oh, we do.